Assalamu alaikum wa rahmatullah wa barakatuh. Today we will cover Unit 7 of the course M256 Software Development with Java. The unit title is Design Decisions. In this unit we will investigate a different design for one of the hospital system use cases and see two different designs, actually, Design 1 and Design 2. We explain some factors that are relevant when comparing different designs and why we would prefer one design over the other. An alternative and invalid scenarios will also be discussed for hospital system, and we'll investigate that matter. We will find how we can and ensure that invariants are preserved and no invariant is broken, means we keep the invariance applied to the objects of our design. Otherwise, we will have invalid scenario. To avoid this, the invariants need to be preserved, and that's what we are going to consider today. We have studied derived associations and derived attributes in the design phase. Now we will discuss how these associations and attributes are dealt with when we are considering the design. Here we need to highlight that the designs we produced in Unit 6 can be revised. Means if you have more than one design for part of your system, especially the dynamic models, you may review the designs available and select ones that help me achieving my main qualities, which are maintainability and reusability. So here we will introduce some basic guidelines and the principles of how to select between designs and select the one that fits your needs more and guarantees better quality in your software. To do that, let us have a look at the use case teams patients. In that use case, we decide that the administrator identifies the team. For each patient cared by the team, the system displays the patient name and the name of the ward that the patient is on. Of course, as usual, and we have done in Unit 6, we will build the coordinating method for this use case, and the coordinating method is get patients and wards. That will return a map of pairs of patients and ward objects, such that for each patient object, a patient linked to a team, the map contains a key value pair of a patient and a ward, where the ward is linked to the patient. This is the boss condition for this method. Here is one design of the object diagram, or a scenario for an object diagram for this situation. We have team 2 cares for patients 3, 5, and 4, and we find that 3 and 5 both are in ward 2, where 4 by himself or herself is in ward 1. This is the scenario. Of course, as usual, we build a walkthrough for the scenario, and the walkthrough is given here. Make it clearer by showing the sequence diagram. Here is the first sequence diagram for the first design. In this design, the interface is requesting or invoking the method get patients and wards, and that method is forwarded to the team 2 with the same name but no parameters. Now in team 2 will itself contact the patients and get the wards for those patients. So he will team 2 has patient 3, patient 4, and patient 5. A message will be sent to each of those patients to get from them the name of their ward. They're supposed to know their ward. So team 2 will collect this information and link and map each patient to its ward and return it to the coordinating object, which will return it to the user interface requesting that service. Now you find that team 2 did the job. The coordinating object has only just to pass the message to team 2, and team 2 will complete the whole job and return the results to hospital 2. In another design that we see in here, you find that hospital didn't forward the method get patient and wards to the team 2. It just asked for the patients from team 2, and the coordinating object has to contact each patient and get its word. So the job now is done by the coordinating object instead of by team 2 object. In this case, team 2 will not do only report what patient it has, and the job will be done totally by the coordinating object. Now, to compare and find out which is better to follow design 1 or design 2, we need guidelines to help us deciding. Design principle, which are the guidelines that we may follow, are meant to guideline us for which objects should be allocated which kinds of tasks and how these objects to communicate. Learning design principles is very important to help us choosing or trying to choose the right design for our part of the system or for our system. But we have to remember that these principles can vary depending on the context. So it's not always one design is better than the other. Depending on the context, if design 1 is good in this situation, maybe it's not as good as design 2 in the different situations. So it's a kind of guide, but it's not always giving you the same results, or it will change depending on the context you are working on. Here we will study 4 basic design principles. The first one is information experts, then the even distribution of responsibilities, and we will cover cohesion and coupling as design principles to decide which design we prefer and which design will give us a better quality in our system. As in the real life, we know that some people know more information about topics than others. Same for object-oriented development. You find that some of the objects are having more information than any other objects in the system regarding that particular task. We call that object an information expert. So sometimes we give the lead and we give the attention and consider that if the object is an information expert, then we may assign the responsibility of perform the task on that object. Comparing the design 1 and design 2, in design 1 you find that team 2 is having more information about the patients than the coordinating object hospital. So if we consider the information expert principle of design, then in this situation we prefer to give the tasks to team 2, because team 2 has more information. Team 2 is the information expert in this particular context. The other principle that we may consider is that we have what we call even distribution of responsibility. In our situation, if we are always going to make the coordinating object do the work as in design 2, then in here in design 2 we find that a hospital object, which is the coordinating object, is doing the job in behalf of team 2. And if we want to repeat that all the time and make the coordinating object do most of the work, then there will be a very heavy load. There will be a very heavy load on the coordinating object. So it's better that we distribute the responsibilities between the objects, including the coordinating object. This distribution will follow one of two terms or mechanisms or techniques. One we call it the forking, and the other one we call it the cascading. Here in the forking describes the situation where P sends a message to Q, as you can see in the sequence diagram, and this message says get R, asking it for R. Now Q returns R to P, so P can then send the message to R asking it to perform its task. So this is a forking mechanism, forking method of doing it. So P will ask for R, and then it will take the reference for object R, and then it deals with it directly. And that's the design 2 sequence diagram. Here, hospital is asking for patients from team 2. Team 2 will give the hospital the patient name, and hospital will carry out the rest of the job. That's the forking. On the other hand, in the cascading, it involves a greater delegation of responsibility. Cascading describes a situation where P sends a message to Q, asking Q to ask R to perform its task. So it doesn't ask for R, it asks Q to communicate with R and get the information done. And this is very much matching our design 1. Okay, so the user interface is talking to the hospital, and the hospital is asking team 2 to talk to patients and to get the information from patients. So design 1 is following the cascading distribution of responsibilities. The other principle is cohesion, and we have covered that in Unit 5, which is a measure of how strongly related and focused the responsibilities of a component. In general, maintainability is and also reusability are made better and can be improved very much with using cohesion, but at the same time you have to be sure that you are not overloading the objects with the responsibilities. Otherwise it will be hard to deal with that object and cooperate with it. Coupling now is also covered or was covered in chapter 5. We are trying to avoid high coupling between classes and situations where classes are depending on each other. This dependency between classes, for example, P and Q, includes the following. Object of class P have an instance variable that's reference, and that reference is an object of or objects of the class Q. P is a subclass of Q. An object of class P sends a message to an object of class Q that's inside one of the P's method. A message is sent to an object of class Q. P has a method that receives or returns an object of class Q. Of course, we are always working and looking for designs with low coupling, considering a desirable feature of software. Actually, this is a very important feature that we always try to achieve, to have low coupling between objects and low coupling between classes in our design. It's more easy to reuse your class. It's more easy to maintain your class if it's having a lower coupling with other classes in the system. If we consider the designs given earlier, design 1 and design 2, and you want to see according to coupling which one is preferable, based on the information given in this slide, you will find that design 1 is preferable over design 2, considering the coupling principle of design. Of course, design principles may relate. They are not separated. Maybe one of them will be affecting to other either positively or negatively. Now we move to what we call invalid and alternative scenarios. There are two different things actually. Invalid scenario is a scenario that's built and it's either not following the design of the class conceptual diagram, or also invalid scenario is a scenario that doesn't follow one of the invariants, so it's break the invariants on some of the scenarios objects. So far we design on straightforward circumstances. We don't take alternative design with difficulties, design with the problems in concern, but in the real development you may need to deal with designs and alternative designs. You may need to deal with scenarios and alternative scenarios, because for every use case there are different possible walkthroughs that the use case may go through. So we have to consider all these situations. To be able to describe and explain the concept of invalid and alternative scenarios, we may have a look at the use case treat patient, which says the administrator identifies the patient and the doctor. The doctor must be in the team that cares for the patient. The system records that doctor has treated that patient. Here is the coordinating method for that particular use case, which is record treatment. It has a precondition and a postcondition. The precondition, the doctor and the patient must be linked in the same team, means they must be connected to each other through the link cares for. And the postcondition, we will link one doctor to one patient. This follows by an invariant that says if a patient is any patient object, then a doctor object linked to a patient is also linked to a team object which is linked to a patient. To be able to build a correct scenario, we have to be sure that we get the precondition, postcondition correctly, and we also be sure that we apply the invariant given here. Here is some valid scenario for the object diagram. The object diagram A is the object diagram for scenario before treat patient 5 and Dr. 3 are not linked, and in B we see them linked because Dr. 3 has treated patient 5. With the valid scenario, as usual, the user interface will talk to the coordinating object, and the coordinating object will call the method record treatment by Dr. 3, and the thing will go just as smoothly as usual. But in other situation, in here we see a valid scenario. Dr. 3 is not connected anyhow before in A to patient 5, and after treating it or treating him or her, now Dr. 3 is connected to patient 5. We have no problem at all because patient 5 is under the care of team 2 and doctor is a member of the team 2, so we have no problem with this. In other situations, for example, in this situation, Dr. 12, for example, cannot be or cannot treat patient 5 because Dr. 12 is from team 7 and team 7 is not the team caring for patient 5, and that will produce for me invalid scenarios. This will stop processing of the method and allow the user interface to handle the exception, providing the user with some relevant information. This information will specify that Dr. 12 is not member in the team that cares for patient 5, and we will not continue the process anymore. Of course, this reporting needs to be put in a sequence diagram, and before that in a walkthrough, and at the end the system will throw an exception, as you can see in step 4, saying that patient 12, so Dr. 12 is not allowed or is not permitted to treat patient 5 because it's not in the team that cares for that patient. As you can see here, you find that the return data types are false, an exception means this process cannot be continued, and patient 5 cannot be treated by any doctor outside the team 2 that cares for that patient. After this, we update the structure model as usual, and we consider the cases where the post condition is giving me false results. On the other hand, we have what we call the alternative scenarios. In the alternative scenarios, we will just use one scenario instead of the other scenario, but both scenarios are valid scenarios. So invalid scenario is something cannot be completed and will throw an exception at the end, but alternative scenario is a scenario that will do the same task but in a different way. As we just mentioned, alternative scenarios is something different from invalid scenarios. Alternative scenarios will continue the process until the end. It will not throw an exception. And in case of the use case and the admit method in a class word, we have the post condition. If there is no word object of the appropriate type with at least one free bit, then the null will be returned. And when we return null, this is alternative scenario. This is not invalid scenario. An alternative scenario, successful scenario, but the result is negative. The result is that we have no place for the patient. So we are not having problem with the development, having problem with running the application. We are not breaking any invariant or not going against the conceptual decisions, conceptual design decisions. We just follow the design as proposed, but we have a negative result. So that's what we call alternative scenario. If you want to admit a patient to the hospital, either you have a place for the patient or you have no place for the patient. Both are alternative scenarios for the same action, admitting a patient. And we have to distinguish between these two concepts, whether invalid is the same as the alternative. No, invalid is a scenario that will break the rules of conceptual model and invariance, where alternative scenario is a scenario that follow the rules but it will get negative results. And this is what will happen in case of we don't have the suitable word in the hospital for some particular patient. We will return null and we will apologize for not being able to accept that patient. This is the scenario, and at the end you find that it returns null, where in the invalid scenario we return fail and false, and exception means something wrong has happened with the scenario. We have learned in details how we are deciding about deriving attributes and deriving associations. We said earlier, as in case of age and birthday, we said that we derive the age from the birth of date, and also we said that in some situations we can derive some associations because of some existing association in the conceptual diagram. Now, in case of derived attributes, we have choices whether we want to implement that derived attribute as instance variable, or we may have the chance to calculate that particular. Of course, in both cases, we need them to have we need to implement them as instance variable. But if you want to do the calculation and derive the value of that attribute, we have two choices: whether we derive the value on the fly, means we at the time of asking for that particular value, we calculate it and pass it to the part of the system that asks for it, or in other cases we may calculate it regularly and save the value to be reused by other parts of the system. So for example, here you find that ward 9 has a capacity of 4. In case that any patient is admitted to the ward, then you find that the number of capacity the number of available beds will be reduced by 1. If any patient checks out or checked out from the ward, then you find that the number of free beds will be increased, considering that we have a maximum capacity of 4 beds. So this calculation of a number of free beds can be done in 2 different ways. Either at the time of admission or checking out, I can update that particular number of beds instance variable, or I can do that at the time I am asked to use that particular variable. I check with the word and find out the free or number of free beds in that particular object. Please note that we have this say that often derived elements are deemed too closely to maintain and are not implemented. This is very important to consider. Here is the walkthrough for the derived attribute to extract and calculate the number of free beds in case of ward either admitting patients or checking out patients. In our case, they are admitting patient 8. This scenario was covered before when we describe how we build new objects and add a patient to a ward. The full scenario and sequence diagram for admit patient is shown here. You can see that patient 8 is accepted in ward 3, and you find that the number of free beds is decreased because of that admission. When we define number of free beds as instance variable, then we have to provide a method get number of free beds. This is very important because the getter methods are very important to be available in every class that we build. But if we decide not to define number of free beds as instance variable, then the whole decisions and the whole scenario will be changed. Here you find the full description of the class word, where number of free beds is defined as integer, and the backslash tells us that it is a derived attribute. Same goes for age for patient student. You find that patient is defined also as instance variable, and it is a derived attribute. The same goes for derived association. Derived associations are associations representing some information determined in an alternative way in the system, and in here we have example of is responsible for as a derived association. If you want to know who is the consultant doctor for some particular object, as in this case, for example, if you want to know who is the consultant doctor for patient 2, then we need to communicate patient 2 to get this information. This can imaginably done this way. It means I contact patient 2 to get the consultant doctor, but patient 2 needs a link to the consultant doctor to be able to know who is that consultant doctor. So if this implementation is responsible for in this diagram is not implemented, then this sequence diagram will not be working. What we do, we need to implement that link, and we'll have this kind of situation. Now patient 2 can communicate its team 3 in this case and get who is the consultant doctor for team 3, because the consultant doctor for team 3 is the consultant doctor responsible of taking care of patient 2. We could say that not implementing a derived association, simplify designs which involve creating or removing links of the association. But on the other hand, you must be able to get all the information if you don't provide an implementation for the association or the derived association. We go back to communication between user interface and the core system, and this is have been covered in Unit 6. We said that the coordinating object will receive some request from the interface, and being the coordinating object for some particular component or some particular system, it will talk to the core system classes and get the information from those core system classes. Now all the information retrieved or reached the coordinating object will be sent back as a result to the calling interface object. Here we will determine what the user interface needs to do in order to write a message or communicate with the coordinating object, and what it will do with any core object that's received as a result from the call. On the other hand, also we'll talk about some of the accessibilities and using them in the implementation phase. Let's consider the use case wards patient. It says that the administrator identifies the ward. For each patient on the ward, the system displays the patient's name and age in year. Now, as you remember, we specified the coordinating method for this use case. It's called getPatients, that takes ward as a parameter, and it returns a collection of all patients objects linked to a ward. In this diagram, we show the sequence diagram for the list wards patient. This sequence diagram shows the user interface sending the coordinating message getPatient to ward 3 and take ward 3 as an argument. The user interface will first need access to all the ward objects. Okay, this is very important in the core system, so that it can supply as argument a ward object corresponding to the ward selected by the user. Now, how this will be done? If you recall that corresponding to the navigation of the association has wards from hospital code class to ward class, there's an instance variable wards in the hospital code that reference a collection of all wards objects. Now it is possible that we provide a method called getWards in the coordinating class host code class, which returns a collection of all the wards objects in the core system, and which can then be used by the user interface to retrieve these wards objects. This is possibly the signature for the method getWards, and the precondition is to return the collection of all the wards objects defined in the system. In action, you find that the user interface now will ask the hospital to provide it with all the wards, and it can call the method or invoke the method getWards by sending the message getWards, and the hospital will send the list of words or the words to the user interface. Now the user interface can select any of these words and can send it messages to get the patient in that word. Again, we may repeat the same situation to make things clearer on another use case, which is list teams patient use case. You have the detailed of the use case and the coordinating method created earlier for that use case. We go through the same situation and we build more objects that can retrieve for us either individual components or teams or collection components, as in case of teams in this situation. Actually, the same goes for this use case. We continue with the same thing. We get methods that be implemented by coordinating object and that can retrieve objects from the core system classes. After we finish these designs, we need to update the structure model by adding more protocols and more links to our classes in the model. As you can see, this is a complete sequence diagram for the treat patient use case. Of course, the interface needs to display some information about the objects in the system, and this information will be taken from the object returned from the coordinating object, or it may be returned as individual values. So for example, you can get a name or get an age or get an object like for example patient 1, and from that patient 1 you can extract any individual piece of information or attribute value from that particular object. Now, talking about accessibility, we have discussed the accessibility earlier, and we said that for the purpose of hiding the information and keeping the integrity of our data, we can use public, private, protected, package access specifiers to control the use and the access for our information. To remind you, we have three kinds of accessibility: public, private, and package. Public accessibility: any class in any package can access a member having public accessibility. This type of accessibility is achieved by prefacing a class member with the access modifier public. On the other side, totally different from the public, we have the private, where only a class itself has access to one of its members having private accessibility. This type of accessibility is achieved by, of course, prefacing a class member with the access modifier private. If you don't preface your class member with any access modifier, then it will be defined as a package, and that's what we call the default accessibility. It's not relevant here to use the package access specifier. In UML, we have some other signs that we use to which means symbols that represents these access specifiers. If you have a plus in front of the class member, then it means this is a public member, where if it is minus sign in front of the object, sorry, from the attribute, then the attribute is defined as being private accessibility. This is the end of Unit 7. Thank you very much. Wassalamu alaikum wa rahmatullahi wa barakatuh.